Okay, so our last official unit of the year is going to be just the rest of Chapter 9, which is not that much really, but we're going to take our time with it some. I'm not going to do 9.7 first, I just don't like the book's way of ordering, the way they ordered it, so I'm going to go to 9.8, which is the Introduction to Power Series. So, we're going to be looking at what are called power series, and then we'll also look at what are called Taylor-Maclaurin series. So we've got like 3 kinds of special series, which are kind of like the most important thing you've ever learned so far, ever in math. They can be tricky, and they're kind of the gateway to all future math. They're like the most important tools in my opinion. And of course, if you don't have the right teacher, sometimes they spend like a week on this. We'll spend like 3 or 4 weeks at least, so pretty important stuff. So what is a power series? So here's the idea. Functions can be represented in lots of different ways. Like you guys have seen since you were little, like the library of functions, right? So you had like f of x was like e to the x plus 2 for like a shifted exponential function, and all the whole library of functions. That's an explicit notation for a function, right? I think that like last year in Calc 1, we learned another new way to represent a function. At least one, maybe even more than one. Didn't we do functions that looked like this sometimes? Like maybe a of x was like the integral from, I don't know, maybe starting at 2 up to an unspecified x value of some curve f of t dt. That's a way to write a function, isn't it? What kind of function is that? What's that mean? You guys not remember the name? Oh, good thing I'm reviewing it.
Is it a differential?
No. It's an accumulating area function, right? So this says accumulate all the area under the curve f from 2 up to whatever x is, and output that value, that accumulated area. Yeah? You can think about that as a function. So that's a special integral function. In fact, you could also express that integral function as using the fundamental theorem, right? You could say that that's the antiderivative at b minus the antiderivative at a. And you could think about it in those terms as well. So that would be another option. But my point here is that functions can come in a variety of forms. Besides just your elementary explicit functions, they can come in the form of integrals. And today we're going to learn that they can come in the form of a series. So a function on the real numbers coming in terms of a series, that should like blow your mind. You should just have mind blown after that, at least a little bit. So here's an example of what I mean, e.g. e to the x. You guys know that explicit function well, right? Like it's one of the most important functions in all of mathematics. Remember, it's really important because in calculus, when you take its derivative, you get that function back, right? So pretty important function. It turns out you can write that as a power series. That can be written as this. So the pattern's pretty easy to recognize, isn't it? And if that series actually is carried out to infinity, you find the sum of the series. The sum of that series is e to the x, the function. Which is crazy. This is the way your calculator does everything. This is the way computers do everything. Remember, your calculator or computer cannot in its head hold an infinite number of values to even be able to do e to the 2. It can't do that. What it does is it looks at this series and decides, we've been talking about error a lot this year, right? So it says, well, what amount of error is acceptable? And it just cuts this series off out here at some point, and it just adds up all those things to figure out something like e to the 2. And it would say, like, basically, when it tells you e to the 2 equals, what it really means is approximately equals, and it's gone like 1 plus 2 plus 2 squared over, what's 2 factorial? 2 plus 8 over 3 factorial plus 16 over 4 factorial. And it just cuts that off in an appropriate spot so that you don't get very much error and you never know the difference. That's how your calculator gets around the issue of having to remember an infinite set. Pretty neat, huh? Okay. So, main idea that we're pursuing now is functions can come in the form of series, specifically what are called power series. Okay, so here's a definition. So the series that goes from 0 to infinity and looks like this or this version of it are generic power series. That's what they look like in general. This is a power series centered at x equals 0. Any guesses on what this power series is centered at? C. This is a power series centered at x equals c. So power series can be centered in all kinds of places depending on their center and what's called their radius of convergence. That determines what the domain of that function is. So here's the idea. Here's the real big idea, which you always want to keep this in the back of your mind as we're going through this unit. And if so, all the weird math we'll do makes perfectly good sense. So our function, which is now in the form of a series, in fact, a power series that can be centered at any c value anywhere, that function is only defined when the series converges, right? If the series diverges, then all is lost and you can't figure out what happens to x when you plug it into your function. Does that kind of make sense? So it's all dependent on where it converges. So here's what I said. I said that the domain of that series function is the set of all x values where the series converges. If the series never settles down to any specific thing, then that breaks down the idea of what a function is. Because remember, in abstract, what a function is a machine called f, and you do what? You toss x's into it, and what pops out? Y's. But one of the main rules of that function machine is if it's truly a function, if you toss an x in, how many y's must come out? Only one. So if this series over here didn't converge on the right-hand side, then you'd get f of x equals one thing sometimes, depending on where you were at and how many terms you'd added up, and something else another point, or it might be infinity, and that wouldn't really make sense either. Does that make sense? So remember, so this, if this was an alternating thing, and you got one sometimes and negative one the other time, or two different, those would be like two different values, right? So that would break down the idea of what a function is. So our main goal in this unit is to figure out how to express functions as series, and number two, to figure out what values of x they'll converge to. And that's going to be called the radius of convergence. Okay, and I think we're just going to use tools we've already known. That's the big idea. So let's have a look. Maybe one more piece of theory. I'm just going to say that there's this theorem in the book, which we could probably pretty much discover ourselves, but it's kind of like a nice guideline to have in the back of your mind, I guess. So it tells you what a power series must do. A power series must do one of these things. So I'm going to use the word either. So in all cases, no matter what power series you have, it has to do one of these things in one. Okay? So a power series can either converge at C only, which means it only converges at its center. That's probably not very useful, right? But that definitely happens sometimes. It can converge what's called absolutely. What do you guys think that means? That's what we want. That's what we're hoping happens. This is what computers use. They can only use absolutely convergent series mostly. That means everywhere for all x values. And that would be all x values pointing to the real numbers. Crazy. So now we can use these natural number defined series to figure out a function on the real numbers. Mind blowing. Every time I think about that, I'm like, man, my mind just is blown. So crazy. Anyway, so they've either got to converge only at the middle, everywhere, or nowhere. Exactly. Oh, wait. My bad. I was thinking nowhere too, though. Or it can be within a certain radius. My bad. Like some R value, some radius of convergence. That would look like something like this. So maybe you had like an interval values, like there's 0, there's negative C, and there's C. And maybe it converges on this end, but not on this end, and everywhere in the middle. Well, then the domain of that function would only be between those two. You couldn't even think about the function as a series over here or over here. So that's kind of the big idea. Okay, you'll see how that goes as we look at some problems. So, alrighty. Whoops, this is kind of wrong. Read this absolute value. Where's this centered? Where's the middle of that?
C.
How far out is it going in either direction from C? There we go. And technically, if this was not there, then this would have to be like that, right? Just being technical with my algebra, really we're thinking big idea here. Sometimes it'll converge on one end, but not on the other end. That can happen. So, alrighty, let's actually do some problems. Hopefully you can do 2 problems today, so you guys can get started working on this. Okay, so here's an example. Got a power series? What's the big clue to you guys that this is some new kind of series that you haven't seen in the previous units?
There's an X.
There's an X. Yeah? There's an X. For what? Why is there an X? Because this is some function f of x. We're not even going to write that down, but we're keeping that in the back of our mind. Okay, I'm telling you, that's a big, important idea. I think this one just says figure out what happens to this power series, and if it has a radius of convergence, what is it? Okay, that's the main theme we're doing. So, does it converge at all? I think we could just apply the tests we already know. Any guess on what test we should use?
Nth term.
Ratio.
Both good guesses. Nth term would be good, but don't you have like a variable here, Paul?
Okay.
Like you've got a variable and then like another sequence index, crazy stuff. So like this x doesn't change in terms of the n for the sum though, does it? So I think we'll mainly just look at the n parts to decide what test to use, and I think Brenda picked it factorial would be a good test for that. So let's look at the ratio test. So if we take the limit of, what are we supposed to do for the ratio test again? Refresh my memory.
A sub n plus 1 over a sub n.
A sub n plus 1 over a sub n, right? So we're looking at that limit. So we're going n plus 1 factorial x to the n plus 1. That n part changes on the exponent changes, right? And then divide by n factorial x to the n, right? Okay.
Plus 1.
So what happens here? We do some factorial canceling, and this goes like this, right? And this goes like this. And lots of good stuff cancels. And we get n plus 1 times x over nothing. Yep. So now think about this limit statement. It's a limit as what approaches infinity? N. This is constant with respect to that, isn't it? And that's the same way we're going to think when we start working on that Calc 3 unit. This is n. X has nothing to do with that. So even though you're thinking x is a variable, it is. With respect to this, it's constant. Does that make sense? So you can just do what with it?
Pull it out.
Pull it out. Perfect. And we're going to do that same thing when we do integrals and derivatives in Calc 3 stuff. You can just remember what's constant, what's not. Just look at what's changing. It's always going to be on the notation. Very easy to do. So what does that one become? What's the limit? Infinity. So this is like x times infinity, which no matter what x is, even if it's a variable, is even if x is infinity, this is still now infinity. So what do you guys think? Yeah. So what are we going to write? So let me write that the right way. So therefore, I said the ratio test shows this power series diverges for absolute value of x is greater than 0, and hence the radius, if they ask us, is r equals 0. Now I said something a little bit weird there. I said the absolute value of x is equal to 0. This does converge somewhere. Yeah. Remember, it's got to be one of the 3 options. It can't diverge everywhere. Power series always converges somewhere. Where's this one converge? If you make x equal to 0 in f of x, that's the series of what? 0 plus 0 plus 0 plus 0 plus 0. Does that converge? It converges to 0. Remember, all power series have to at least converge at their center. And this guy is centered at 0. There's no x minus c there. So let's write that down. So this guy converges only at its center of x equals 0. So that's why its radius is nothing from that point. Okay? And all power series have to at least converge at their center, which is usually not very useful, but true. So in other words, the domain on this guy, the only thing you can plug into this to make it make sense in terms of x values is 0. All right, let's do one more. Oh yeah, just enough time. One more so you guys can start working on this. Okay. Another power series, same directions. So I want to figure out, does this converge and what's its radius of convergence? Wow.
Can you take a root test?
Yeah, you could. I'm going to tell you though, the test you probably want to use on almost all of them is ratio test. Root test would work though, you're right. Totally. So I'm just going to go ratio test. Oh, can we go like this too? We could pull out that 3 if we wanted to, right? Yeah. I guess let's just leave it. You could probably do it either way. So let's go 3x minus 2 to the n plus 1. It's going to cancel out, isn't it? Cancels out. We get this if we simplify, right? That's all that's left.
Yeah.
Is there any n in there?
So it's equals x minus 2.
So just equals x minus 2. On the other one, since we got infinity, we weren't very careful about what we concluded at the end. How does the ratio test work again at the end?
It's greater than 1, then it diverges.
It's greater than 1, it diverges, which we got because it was like infinity, right? Except if you plugged in 0, it wasn't. That's why it worked at 0. And if it's less than 1, it... So we should put like this here, really, right?
Yeah. You can just solve for that.
Exactly, exactly. So now we've got like a little inequality there. We don't really need this equals anymore. And we can find the radius of convergence from just thinking about that inequality. So I like to think about these as a picture. You guys might remember this, though. I don't know. Do the inequality however you want. That means this, yes? And you add your 2 on all the sides.
That's like 1.
Yes. And there you go. You've got your radius of convergence. So therefore we'd say, I'm going to try to do one more example before you guys leave, so we have another one. But I'd say, therefore, my power series up here, which is centered at what?
2.
2, which by the way, look at this. Isn't this 1 to 3? That's centered where?
2.
At 2, should match. This power series that's centered at 2, by the ratio test, converges between 1 and with a radius of, what's the radius here, I guess? What's r?
1.
R is 1. Yeah, but that's the actual places where it converges, which means the domain of this function, that function only makes sense to think about between 1 and 3, and you can't even include 1 and 3 on the edges, or it breaks. The function breaks, and it doesn't even make sense to try to think about it. Does that make sense? I think we should try to work one more problem here. You guys okay with that or not?
Sure.
Because I'm going to give you a shorter assignment due Wednesday, so I think you want to get started. Okay. One more for today. Okay, so I'm going to try to go through this guy a little bit quick. Let's see, same question though. Where does it converge? What's the domain of the function? It's never going to say what's the domain of the function, but that's how you should really be thinking. Use ratio test. That one screams ratio test, right? Exponents and factorials. So I could go like this. What is that going to be if I put in n plus 1 right there?
2n plus 3.
2n plus 3? Yeah. And then down here we're going to have 2n plus 3. Yeah. It's kind of a pain. Times, so what's up here then? 2n factorial, 2n plus 1 factorial, negative 1 to the n, x to the 2n plus 1. Yuck. Even though these look yucky though, as you guys showed me on your test, they're not very hard, are they? Just go like this. Man, what goes here? I remember 1 or 2 people had little issues on that.
Plus 2.
There we go, right? We good? Rhino, you okay? We're almost there. This guy's gone. Oh, I should write this. I should have left one of those like that, shouldn't I? So that we can cancel these guys. That guy's gone. Absolute value of negative is going to make that guy go away, so what do we have left?
X squared.
X squared.
Over 2n plus 3 over 2n plus 2.
X squared can be factored out because it doesn't have an n in it. What's that limit go to? And for the ratio test, what are we testing? Like if this thing is less than 1. So what's any x value times 0? So what's that mean?
Converges everywhere.
Yeah, this guy converges everywhere. So this is a really nice thing. You could totally represent this with a function everywhere on the real number line. Very nice. Which is crazy, right? Like how it's just mind blowing. But we're going to look at exactly how. So let's see. So therefore, our series converges with a radius of convergence equal to infinity in either directions. Let's see, did I say anything else? No. Yep, that's all I put. On the whole real line, f of x equals the power series is defined. Okay, add that. Okay.
Should we be thinking about these graphically? Because I'm kind of having
We're
trouble
tired.
figuring out what the graph of this looks like.
Not yet.